Hello fellow learners, today we are embarking on a unique journey into the captivating world of learning manifold in differential geometry. Think of learning manifold as embarking on a grand adventure. And what is the first thing you need of any epic quest? The right map. Yes, in our case, these maps are the books that will guide us through the labyrinth of manifold. But we all learn differently, right? Some of us prefer notes, lecture notes, compact, coin size, tailor-made to specific courses. If you're someone who thrives on visual explanations and engaging tutorials, YouTube is your treasure trove. So in this video, we are going to discover all of these. Best lectures, best books, best YouTube videos, and some of the core fundamental concepts which are crucial in your learning process. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this new video, Lesson 23, How to Learn Manifold. Before we go ahead and learn the concept of manifold, there should be a reason that why we are learning. Moreover, I would say, why do we need a manifold? First, we will discover what is the real need, what is the basic purpose that we are studying a manifold. But before going ahead, here is a quick and an important good news for you. That is on 29th of this month, there is a free webinar which I'm conducting on Einstein's general theory of relativity. Yes, it is absolutely free, and this is the date and this is the time, 29th of October, 8 p.m. Indian Standard Time. There will be a free webinar which you are welcome to participate on Einstein's general relativity. It will be conducted via Google Meet. So in order to register, all you need to do is to write at this email ID, write a little bit about yourself and mention your WhatsApp number. Remember, it is not that you have to be a science or a math graduate. You can be anyone who is curious to learn about Einstein's general relativity, and this is a very intensive webinar which is conducted absolutely free of cost. So those who are interested, please do write to me, and I will see you on 29th of October starting 8 p.m. Indian Standard Time. And now it is the time that we should explore that why do we need a manifold. Now the reason is that starting from a toy or any kind of a structure like a soccer ball or anything like a building or earth or anything, you will see that there is always a surface, or I would say it causes a kind of a curvature on each of these manifestations, each of these structures. So what I'm trying to tell is that all these objects need a surface, and manifold is nothing but it is basically a kind of a study of these surfaces. How it is bent, how it is curved, how it is going this way, that way. So manifolds are basically all this structure starting from a soccer ball to a building or any engineering construction. Anything that we see is requiring a surface, and manifold would give us a thorough, scientific and a rigid understanding of what these surfaces and objects that are standing on the surfaces about their characteristics. So here is a quick definition. Differential geometry is a branch of mathematics that deals with geometry of curves and surfaces. So you see, this is a kind of a curved surface, and the entire physics, if you're talking about physics, because differential geometry and physics are very intimately related to each other. If you consider motion, force, electromagnetism, everything, this takes from here to here. So from a curved surface, which is the manifold, which is the subject of our video today, we are taking from this curved surface to the physics. But it should not be the other way around. That is not from physics we will come back to the curved surface. It is better that we study the manifold, the characteristics, the features of the manifold, and then we go from there to the particular physics. And this is true for Einstein's general relativity and various other science or theories which considers manifold to be important. So we get a curved surface, and then we get the entire physics of motion, force, electromagnetism, gravity, everything happen on it. And so the sequence is moving from the curved surface to the physics. Now you see this being a curved surface which is immersed on a kind of a flat Euclidean space. So why do we need a manifold? Because we can differentiate, and that is why we need calculus. And in general relativity you will see that is why gravity is caused due to local curvature. And this is because all of these are local in nature. So we will see in my other video which I have made on how general relativity and differential geometry related, gravity is basically due to the local curvature. So studying manifolds, studying curvature, studying the local nature of this actually helps to know more about the physics. This is local, and for the global structures all we need is basically a kind of a study of a topology. So this actually tells that why do we need manifold, and especially in general relativity and the theory of gravity, the understanding of manifold is very crucial. Here is a quick understanding of how general relativity would be related to, I would say, differential geometry. We know that gravity is not a force, it is a fabric. Space-time is a four-dimensional fabric, and mass and energy actually causes the curvature, and general relativity is consistent with special theory of relativity, which primarily deals with the speed of light. Now you see on all these right hand side four definitions, curvature and fabric and curvature, these things are very important. So all these definitions emphasize upon one fact, that is the curvature. So we are dealing with more with curvatures, be it differential geometry, be it general relativity or anything like that, and that is why we need to study manifold. Okay, so here we come to the next part of our understanding, that what is a manifold. Now that we have understood that why do we need a manifold, the next point is that what is a manifold. I will just quickly give you a basic idea, very simply, coming in the next part of the video. What is a manifold? Now you see, generally manifold comprises of two words, mani plus fold. And if I go back a little bit literary side, then these are actually amalgamation and assimilation of few of the words which are Northumbrian, some of them West Saxon, Dutch, etc. So this comprises of mani, which means basically numerous different parts, elements, features, etc. And fold actually means to bend over itself, or wrap or furl or bend or ply on anything. So we get many, that means different kinds of features, elements, and on the other side we get the meaning of fold, which is bending itself. So we can say that manifold are topological space which deals with numerous shapes and forms that are bent, furled and wrapped, and that is why we need to study their characteristics. Here is a quick understanding and a definition of manifold. Every point in a manifold has a small area which looks like Euclidean. This is very important. It should look locally like a Euclidean. This is a kind of a strict definition, that manifold is a topological space that is locally resembling a Euclidean space near each point. Now this is a kind of a definition which we go through English, but what about showing it on a graphical and a schematic diagram? Won't that be easy? Let us look into the next part of the video. Suppose I'm standing right over here on a globe sphere. I am watching this right from the top, and I'm trying to move from each point of one to the other. So I move from one place to other and to another. Now what I do is that this same movement I'm tracking or I'm plotting on a curved surface which fairly looks like the same, and here also I am moving through the dotted points and come back. So what I see over here is that the global surface locally looks Euclidean space near every point. So this is a global structure and this is a local structure, and this is the basic identity or the special feature of a manifold, that whatever the way, whatever the things that we are doing on a global surface, once we zoom and zoom and zoom, that looks locally Euclidean, and that is what makes a manifold. So here is the structure. These geodesics are converging to a certain point. We call it positive curvature. These geodesics are moving parallelly, so there is a zero curvature, and these geodesics are traversing a void and they are not meeting and diverging, so they are called a negative curvature. So each of those sphere and the hyperboloid, if I try to plot it on a kind of a flat surface, Euclidean surface, then all I can do is that differentiate and further differentiate using calculus and apply the rules of calculus on the manifold, and that brings us the feature of a manifold. So on the right hand side what you're seeing is basically kind of a magnification of the sphere, hyperboloid and the cylinder, and that is why we call it as a manifold, because we can use the rules of calculus and the calculations becomes fairly easy. So all these yellow things that you see on the left hand side bottom of your screen, it shows that it locally looks Euclidean, although it is not, I would say, Euclidean, it is fairly curved surface. So from here, where do we go? We move on to the page, and what we can say is that all those yellow boxes where we apply the rules of calculus can be extrapolated into something which is called a real number, which starts from x1 to xn, and we can call them, they're locally isomorphic to the Cartesian plane Rn. So this is how we define a manifold. All these are applicable with the rules of calculus, and they're not equal, but technically we should call it locally isomorphic to the Cartesian plane or the Euclidean space. However, if you're willing to learn more about manifold, go to this video. Each of these boxes when zoom looks like locally isomorphic. You can go to this video, lesson number 19, Beginner's Guide to Manifold. I've explained much more in details of the manifold. So we have understood that why do we need a manifold, and specifically what is a manifold. Now it is a time to look over one very crucial and an important concept which makes a difference in our learning process of manifold, and that is coming up in the next part of the video. We call it smooth manifold and a differential manifold. Why do we need it will soon become clear, but first let us understand a kind of a distinct feature and kind of a comparative study between smooth and differentiable manifold. Well, first of all, a smooth manifold and a differential manifold, we call it smooth because it is not only topologically a Euclidean space but allows for smooth functions. Differential manifold, I would say, is differentiable, is similar to a smooth manifold, but it is little more flexibility. It allows for differentiable functions, which means you can take at least one derivative. What we say is that smooth functions are those that are infinitely differentiable. That means we can take derivatives of first, second, third, fourth, and so on. But here we can take at least one derivative. This means that the curves might have some kinks or sharps or turns, etc. But again, these are differentiable. This is a very crucial concept before we go ahead and understand what is a manifold. So a pictorial description would give you a better idea. So here you see the surface of the sphere is a smooth manifold. This is surface of the sphere because we can quickly move and we are smoothly moving from one part to the other. Whereas this one, the edges of the cube is basically a differentiable manifold because the definition itself tells that there might have some kinks on sharp turns, but these are differentiable at those points. Very important concept to understand, and you will soon see why I am telling this. So here is a comparative study. Smooth manifold is something which is a special type of a differential manifold where all function must be smooth. That means obviously it will be infinitely differentiable. Differentiable manifold or a differential manifold would be for functions that are differentiable. That means you can take at least one derivative of these functions. Smooth manifolds are more restrictive because they require a little bit of higher level of smoothness. Differential manifolds are, I would say, much more general because they accommodate broader range of functions. Also, in a smooth manifold, the transition functions between the charts basically are infinitely differentiable by the definition itself. And in this concept, the transition functions charts must be differentiable. So here is the ultimate crux. What I'm trying to tell is that all smooth manifolds are differentiable, but not all differentiable manifolds are smooth. And the reason is this one. Smooth manifolds are the most well-behaved, allowing for smooth functions. Differential manifolds are more general, I mean to say more wider, and allow one function with some degree of roughness. Just as I told, the edges of the cube, there's a kind of a roughness, there's a kind of turn, there's a kind of a kink. So where you can take at least one derivative. It is all about the level of smoothness, and there's something which I've omitted which is called a differentiable structure, which is not a part of the video. So remember, all smooth manifolds are differentiable, but not all differentiable manifolds are smooth. Now from this concept of smooth and differentiable manifold, we come to the next concept which is equally important for us to understand, which is this one, which is called a smooth function and what is called a differentiable function. Now, why it is important? Because all this smooth and differentiable manifold depends on the smooth and differentiable function. So again, it is quite more or less similar. A smooth function is one that is infinitely differentiable, meaning it has derivative of all orders, whereas differentiable function is one that can be differentiated at least once. That means it has a first derivative. This is denoted by C infinity, which means that it goes on and on and on, and this is denoted by C1. Also, you see, these are some of the examples of smooth function. These are some of the examples of differentiable function. So if I take this kind of an equation, what do I mean by this is that this function is differentiable infinitely many times. This means that the graph of the exponential function is smooth and does not have any sharps or breaks. So you can see this is a graphical representation of what is a smooth function and a differentiable function. It is very important in our learning of manifold. So here it comes. In summary, a smooth function is one that is infinitely differentiable and exhibits no abrupt changes or singularities. Differential function is one that can be differentiated at least once, but it may not be smooth and may have kinks or corners or turns. Now the question is this one, that how does it affect in our learning of manifold, and why is it important? Does it really make any change in terms of a learning a manifold, and is it just a concept? Definitely yes. That is what I am going to tell in the next part of the video, why it is important in our learning for manifold. So the first thing is that we need to understand that going from smooth to differentiable, which one we should learn first. And for that I am going to give you a very easy comparative analysis, and the answer will come from yours itself, from yourself. You see, smooth manifold we can define using calculus, derivatives, integrals, etc. Differentiable manifold, I would say these are concepts which is a little bit difficult. Also, the examples you see is a sphere, torus on a Euclidean space, but on a differentiable manifold you need to deal with Mobius strip, projective plane, which are quite, I would say, advanced concepts. Also, the application for smooth manifold in physics, engineering and differential geometry is quite widespread, but differential manifold is mostly on topology and differential geometry. It is easier to understand and it is more difficult to learn and understand in terms of differential manifold. Further, we see that in smooth manifold, the calculus, the concepts are quite easy to define, but it is not so easy. Also, in differential geometry, concepts are easy to define and calculate, but here differential geometry concepts are a little bit difficult to define. You see, smooth manifolds also have a, I would say, a much more intuitive and easy to define and visualize, but differential manifolds that are not smooth can also obviously would be difficult to visualize. Also, you see, the textbooks that we will see from now on in the video contains more about smooth surfaces, smooth manifolds, etc. That means the availability of resource is very much, and here the textbooks about differential manifolds that are not smooth are not, I would say, it is there but not too much. So from here you can obviously get an understanding that when you're learning manifold, which approach you would take, smooth manifold and differential manifold, you really got the answer. Now we come to the central part of our video, that is which book you would select in terms of manifold. Coming in the next part of the video, I would show you and justify and tell you what are the best books of manifold to select. Okay, so the first book that I would select would be this one, which is called An Introduction to Manifolds, and it is written by Loring W2. And this is 88%, you can see, amazing, 5 stars, and this is a Springer publication, contains around 410 pages, and this is Loring W2, is a Taiwanese American mathematician, attended McGill University, completed his PhD and doctoral under Philip A. Griffiths. So let us go now into the content or the what the book contains all about. First of all, a quick review. You can see all of them are absolutely great, very easy and interesting book. And then somebody said this book taught me how to calculate RAM cohomology, great text and exposition. So I think I really don't need to define further. So straight away let us go into the context of the book coming up in the next part of the video. So you see it starts again with smooth functions right at the beginning. So that is why I told you that we need to understand which way we will go. However, differentiable manifold books are also available, but it shows. Then it goes into tangent vectors, exterior algebra of multivectors, covectors. Then it goes into differential forms. So you see, before coming in chapter 2 or the part 5 of manifolds, the book has taken a lot of energy and a lot of inputs regarding the preparation. Then we come to manifold, smooth pipe of manifolds, quotients, etc. Then it covers something which is called a tangent space, which is very important, submanifolds, the categories and functors. Then it goes into tangent bundle, bumps and partitions, and the Lie group algebra, Lie algebra, and differential forms. And then it finally goes into exterior derivative. Then chapter 6 goes into integration of manifolds, orientation, and then the DRAM theory or cohomology. Then it goes into homotopy, and then finally appendices, which contains certain things which you can ignore, the point set topology, etc. Okay, so what sets this book apart? I mean to say, why I'm selecting this book only out of the many books which are available. The reason is that you will see that first, the book comprises very well and a very good solid foundation of Euclidean spaces. As I'm lecturing a lot of areas into differential geometry, into my webinars, etc., I constantly tell that Euclidean space without a solid understanding, it is difficult. So smooth functions on Euclidean space, tangent vector, derivations, vector fields, and then this divergence, convergence, all those things are being extensively covered, which gives a very good solid foundation. Next comes a very important concept called exterior algebra. Not much I have seen books which cover up exterior algebra. This book covers up exterior algebra, including tensor product and wedge product, which is very important in terms of understanding manifold. A very advanced but a very difficult concept, sometimes become difficult for students to get over. It is called differential forms. So the exterior derivative and the differential forms is extensively covered in this book. Apart from that, a brief history of manifolds, as you can see Bernard Riemann's photograph. Then the manifolds, the topological manifolds with very nice diagrams and easy mathematical equations is being covered. Then it comes to smooth map on manifolds, smooth map between manifolds, and things like that. It further covers a very important and favorite topic of mine, which is called the diffeomorphism. It covers example of smooth mass, the inverse function theorem, and these are beautiful diagrams. There is no haziness, there is no pencil marks, etc. These are absolutely clear, I would say easy and very easy to cover up. Now you see, this book actually covers manifolds first of all in this way. Then it covers smooth map of manifold and then the quotients. So before covering manifold, it covers a lot into the foundation and then part of the manifolds. The tangent space is also covered in quite of details. Some of the books I have seen, they ignore tangent spaces, but not for in this book. It will cover submanifold, category and functors, tangent bundles, bump partitions, C infinity bump functions, and all those. So this is something which sets the book apart. Then the Lie groups and Lie algebras, it is covered quite extensively in details. So that is something really great. And then, as I was talking, differential forms, starting with the cotangent bundle, then the differential K forms covered by exterior derivative, Lie derivative, and intermultiplication. So this is something which is very striking, very important, and each of the concepts I just showed you how it has been covered in very extensive details here by not using very difficult equation, and that is the reason what sets the book apart. And finally the integration part, which includes the orientation and integration on manifolds. So now the question is that if you talk of the DRAM theory, this book actually covers, I will show you another book also which covers a lot of DRAM theory, but this book, as you can see, it starts with cohomology and then homotopy and variance. It's just absolutely great. I went through the book. I can tell you it will be a very easy walkthrough and a very good adventure that you will really enjoy learning and going through this book. Okay, so if I take this book, what would be my honest review? I would say it is a very well arranged book and very well designed. These book's concepts cover up the foundations of before going into manifold. It is very simple, I would say, language, and the equations have not overtly, I would say, made complicated. It's very easy and one of the best books and easy to understand in learning manifold. So that is all about an introduction to manifold, but I won't rest right now just covering one book, but it's another a very important book which is coming up in the next part of the video, which is called this one, very famous book of John M. Lee, which is called Introduction to Smooth Manifolds, 78% 5-star, and the book is around 708 pages, very extensively, and this is the photograph of the famous John Jack Marshall Lee, American mathematician, who is specializing basically on differential geometry and graduated from Princeton University. There is no point in talking much about John Lee. We all know he's a great mathematician, great writer, and has contributed significantly in differential geometry. But I think that before going ahead for any book or any understanding, a little bit of understanding of the author, who is, and a visual photograph actually makes sense. So let us go directly into the book. Well, these are some of the reviews. Again, I'm skipping because there's no point in showing this, because we all know it is one of the greatest book ever written in differential geometry. So these are some of the reviews which I've picked up in Amazon, and it shows that this book is absolutely astounding. So what is the content of the book coming in the next part of the video? It, as usual, again start with smooth manifolds, smooth maps. So again, so you understand, you need to understand and go through smooth manifolds. Then it covers of vector fields and vector bundles, things like that, and cotangent bundles, submersions, etc. It's more or less, I would say, same, but you hold on, there are some important parts which is different from the other book of Introduction to Manifold. It covers Lie group actions, embedding, approximation theorems, tensors, differential forms, and so on. Okay, so it further covers orientation, as I told you, DRAM cohomology and the DRAM theorem, and then the integral. It is very detailed, as you can see, integral manifolds, foliations, Lie group algebras, so on. So now the thing is that once you go through the book, I would like to read a few lines, because you need to understand how this book and for whom it is written. Follow these red lines. So it is a first year graduate text on manifold theory, and it is assumed that the students would know general topology with the fundamental group covering spaces, etc. This book is similar in philosophy to the scope of the famous Spivak's classics test, though perhaps a bit more dense. It also writes over here that I try to keep the approach as concrete as possible, with pictures and intuitive discussions of how one should think geometrically about the abstract concept, but without shying away from the powerful tools that modern mathematics has to offer. That means it's a book for somebody who is a first year graduate. It is a book which covers a fundamental group covering spaces. It would take an approach of Spivak's classic differential geometry book, and it will take also the intuitive understanding but also the mathematical part, and that is something a really good part of the book. Well, I won't run through the entire content of the book, but what I would like to show you some of the things which is not covered in the earlier book, and is very important. So this one, which I tried to make a video earlier, submersion, immersions and embeddings, this is wonderfully covered in the video. As you can see, it starts with beautiful photo, I would say, illustrations of embedding of the torus on R3, and then the constant maps, ranks, connected sum, and all those things. This is very important. Next thing which is important is tensors. Algebra of tensors is covered, covariant tensors, contravariant tensor, tensors on theory of manifolds, and most importantly the Riemann distance function. This is, again, it is not extensively covered in the first book. Also, differential forms a little bit different from the first book, because it starts with the geometry volume measurement and it goes into differential form. It covers of symplectic forms also. Now, if I take both the books, and you would say me the which one to, both of them are absolutely brilliant. They are great books. But I would say to start with this one for those who are starting right at the beginning, because that would give you a fairly easy understanding of manifolds, because this is much more, a little bit more on mathematical in nature. Now, apart from the study of manifolds from books, because books are basically written, keeping in mind a kind of an audience, kind of a knowledge, etc. But what is also important is that what about the lecture notes on manifold? Because lectures are written something totally different, customized and much more easier, expanding on a topic, isn't it? So let us find out what are the best lectures which are available on the internet to study manifold, coming up in the next part of the video. What are the best lectures on manifold? And I can tell you that I'm giving all those links in the description because these are all authorized university links. You can very well go download and read them. First with the University of Notre Dame, and this would be on Liviu I. Nicolescu, and the book and the lecture note is called Lectures on the Geometry of Manifolds. This is the hyperlink which you can go and download. This is a little bit about the author and the professor, who you can just visit his I would say this URL and find out more about his research area interest. So Lectures on the Geometry of Manifolds. Now why I'm saying, you see, it is I think 709 plus pages. It covers of manifolds, natural construction and manifolds, calculus and manifolds, Riemannian geometry, a lot. Elements of the calculus of variations. I'm to say I have just summed up, otherwise it would be a too long of a video. Here you can see the entire spectrum, 649 pages till now, but I have omitted the other pages. So it is a very good, and I have taken a lot of notes. I think that it would be a very good learning if you go through the best lectures of Manifold. This is absolutely great. I'm giving the link below in the description box. Go ahead, feel free, and you can read this one. The second would be obviously the evergreen MIT open courseware. This is called a Geometry of Manifolds. This is the URL, and it is very extensive. As you can see, all the PDFs are free. You can download, you can read, and it's absolutely wonderful. So you can see it starts with chapter 1 and covers up to chapter 35. All the PDFs are there. So MIT open courseware, I think that I really don't need to tell much. These are absolutely great, easy notes. You can download it from ocw.mit.edu. These are available not only differential geometry but physics, mathematics, electrodynamics, a huge lot. So that will be another important lectures on manifold, very easy and very quick to understand. Another would be from the Radboud University. As you understand, Alicia Castro came from Radboud University on a YouTube live speaking on gravitational I'm so sorry, about quantum gravity. So here is the link for the lecture, and this is also quite good. I mean to say, it is lectures on manifold. It starts with smooth maps again and then goes into topology, etc. Lecture 7, 8, 9, 10. So it is around 150 coin-sized version, but yes, absolutely great. So these are the 3 lectures which I would recommend. Other than the books, it would be fairly easy for you to go ahead, study and understand. Now all these are basically learning through books, writing, etc. What about if you're dynamic and you want to really know what are the I would say YouTube videos, because we learn a lot of YouTube videos and I make YouTube videos. So let us see what are the best lectures which are available on YouTube about manifold, and I'm also going to tell you which are my favorite lectures. So coming up in the next part of the video, best YouTube lectures on manifold. Okay, so the first thing would be YB Maths, right? This is the URL, I'm going to say the YouTube URL, and this has got a good amount of videos. You can see 21 videos on topology, manifolds and differential geometry. Absolutely astounding, absolutely great. You can go, you can watch, and he has got a funny dog sitting around him, and he explains this video absolutely great, simple understanding, and you can see you can go into manifolds, but you can see a huge amount of lectures which are absolutely great, and I can tell you this is absolutely great learning. The second one would be the bright side of mathematics. Now this is the YouTube URL, and this is also good because this is my favorite. I'm going to say I have watched many videos. This is a complete playlist. You can see there are around 25 videos only on manifolds. Now the earlier one, if I go back, you see this is basically on topology, manifolds and differential geometry, 21 videos. But here you can see it is basically a sum of 25 videos exclusively on manifold. The bright side of mathematics, the good part here is that he covers a lot of stuffs into I would say pictures, a lot of colors, a lot of animations, and it's a fun and learning. So this would be my recommendation, a very good channel, and which has got absolutely great videos on manifolds. The next one which I would rave would be, I really don't know the channel, but I've given the link. This is a wonderful video on manifold, and this one is also a great video on manifold. Lectures of a person, I think is from IISc Bangalore. I don't really remember, but these are the two I would say separate videos, not for a channel, but you can go ahead and watch it. Absolutely great videos. Link is there. Now, Dr. Robert Dave's tensor calculus, you might know him as quite a popular figure, making videos on manifold. So here it is. This is the YouTube URL, and these are again around 12 videos, quite good on tensor calculus. You can just go ahead and watch it. The next would be, I am quite impressed by the, work of art. This is called Manifolds in Maryland. And this has got my favorite, I would say, this is absolutely my favorite. And this has got a lot of videos. I would say not much, sorry. It would be around 5 videos, but very good in terms of understanding of manifold. It is clear, it covers a lot, it contains a lot of animations. The fonts are easy, it goes slow and makes you understand everything. My favorite, Manifolds in Maryland. You can check. The next one, as usual, nothing to tell, is about the IISc Bangalore, and this has got a lot of videos, and you can see this is around 69 videos on introduction to smooth manifolds. You can just go ahead and watch it. It contains a lot of, it's a conventional learning, so nothing to tell about NPTEL. It contains some 69, is the highest number of videos, I think, exclusively done on manifolds. Next also is a wonderful channel which is called Undergraduate Mathematics, and this is the YouTube URL, and this is on differentiable manifolds and contains around 30 videos. So as I told you, from smooth, if you want to graduate after learning smooth manifold into differentiable manifold, this is again a very good channel, very good inputs, very good lectures on differentiable manifolds. 30 videos, this is the URL, you can go ahead and check it. The next one and the last one would be Daniel Chan Maths channel. This is absolutely incredible channel. This is the URL. Don't worry, all these URLs are there in the video description, you can see. And this is one of my absolutely favorite. And the way Dr. Daniel explains over whiteboard, it is astounding. He has got many other videos on differential geometry, etc., but these are 6 great videos. As I told you, you see, it follows absolutely the way I have been describing on the books, the line integrals and the differential forms, Stokes theorem and the manifolds. So this would be one of my favorite and best YouTube videos on manifold. So well, that's it for today's video. I think we can summarize what we have learned. Why do we need a manifold? What is a manifold? Smooth and differentiable manifold as well as a function. Which book we need to select the content. Then we saw John M. Lee's book and the content of the introduction of John Lee's book. The best lectures on manifold, which is an add-on, and the best YouTube lectures, YouTube videos on manifold, which are available. All the links regarding the notes, regarding the videos, regarding all those things which I talked about is there in the in my description box of this video, so you can go ahead and check it. So that's all. I think I have covered up all those related to video. So I would really like to thank you from the core of my heart for watching this video. If you have liked, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID and this is my other channel on general theory of relativity. You can further follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with a lot of other videos, interesting ideas and interesting, I would say, stuffs related to videos and physics and mathematics. Stay tuned, keep watching, do subscribe, and thank you very much. See you very soon. Goodbye.